Recording now. Okay, cool. Doesn't look like it's not working. Okay. So, week 4, your midterm is next week, and we've gotten, so to recap, in week 1 was timber properties, week 2 was tension compression of members, week 3 was bending, and serviceability. You have to excuse me, I've got a bit of hay fever, so I'm gonna be like sniffly and stuff like that. Um, But yeah, so this part of the course is where the standards start getting a bit weird, in my opinion, and you really start to notice that it is like written differently compared to steels and concrete. Because in my opinion, it's written a lot more annoyingly. What I've prepared here, fuck, believe it or not, it's 23 pages of notes. This took ages to prepare. What I prepared here was what I wish I had done when I was doing the course in terms of how I organize the notes, because I think this will be the best way to jump back and forth between the notes. Because if you do it just from the standards, you will take like an hour just to do one question. Because you like how this how the standards send you about is like, okay, it's like, okay, we're in chapter 4.1. Refer to, I'm just making up numbers by the way. 4.1. Refer to section 4.4.6. Okay, then refer to appendix H8, like, and then back to 4.2, and then fucking they just send you everywhere. It's really annoying. For the connections part of the code, I think it's like quite awfully written, to be honest with you. But anyway, hopefully I can clarify it a bit for you guys here. So we're going to be talking about connections today. And if you've done steels, you'll know what I'm talking about, but I'm talking about another word for connections is like fasteners. So things that are going to essentially hold two different members together, two or more different members together, right? So for small connections, we have nails and screws. This is what's covered in the course. For large connections, we have bolts, and we also have coach screws. So I'll explain what those things are in a second. There's also two types of connections in terms of what they're actually doing, which I'll get into, which is shear and tension. Tension is sometimes called withdrawal, but that's the TLDR. Just unmute in the Discord or drop a message in the chat if you have any questions. Okay. So we have, like I mentioned, for small connections in this course, it's nails and screws. For large connections, it's bolts and coach screws, right? Like it might seem like they're essentially the same thing, but they're actually quite different in. They're similar but different. They have different applications and different strengths in different directions. And yeah, like how expensive they are. They're all pretty cheap, but like how they're installed is quite different too. So the main advantage of a nail is that, well, okay, if you do it the old school way, you get a nail, you get a hammer, you bang it in. But there's nail guns, right? So you can use a nail gun and pressurize air, and is a very quick way of connecting members together. This is done a lot in like roof sheeting. So this isn't really for timber, but roof sheeting or shingles or whatever. You nail those in, and if you did that with screws, it'd take forever. Nails are very quick. So yeah, one advantage of nails is that they're essentially the cheapest and fastest way of doing something, of connecting members together. But you'll see in a second what the kind of drawback is. Screws, you can do it in two ways. You can just essentially have a power drill, or you can use a screwdriver. Okay, let's just say one way is you can use a power drill, which is the electronic one. And you have a Phillip head drill bit, and you can just drive that into a bit of wood. And specifically you need a power drill because you need enough torque to be able to wedge the screw in. So if you use a screwdriver, like I was like alluding to earlier, essentially if there's no hole there, like you're not going to have enough torque with just your hands to be able to drive the screw in, right? But if you do have a hole there, aka if you pre-drill it using another drill bit, like you can pre-drill the material out, like the timber out, and then it can technically go in with a screwdriver, or you can use a power drill with the Phillips head to drive it in. So if you pre-drill it, it takes longer, right? So if you're installing a bunch of these, that's inefficient, but you'll have less material being displaced, right? So let me just draw a little bit, right? So if you have a bit of timber like this, and you want to put a screw in it, like that, right? You can either force it in, right, using the power drill, or you can pre-drill a hole out. You remove that material. Actually, how you do it is you want this length to be less than this length, right? So let's say L1, L2. So you want L1 to be less than L2. This is not really like in the course, but I just like talking about this stuff. So you kind of drill that in so that yeah, it has something to sit on in the end, and that's the least amount of material displaced. So what I mean by displaced is because you pre-drilled it, there's no wood being pushed out in either direction, so there's less like stresses that you're imposing on the material. And then we have bolts and coach screws. So I'm going to talk about coach screws first, right? Because coach screws are essentially just big screws, like big fuck off screws, right? And yeah, like essentially you need a hex socket drill bit and a power drill to drive this one in. So if I draw it out, right, maybe that's what it would look like, right? So that's your power drill. You need like the hex socket, and then that's what goes over the hex head, like that, and that's what you would drive into your timber or whatever, right? Similar idea, you could pre-drill it if you want, etc. But a bolt, right? A bolt is actually fundamentally different to the rest, because a bolt, it doesn't have the sharp bit at the end, essentially, right? And it relies on having a nut, essentially, which is this one here, this bit, on the other end. So if you have two bits of material that you want to bind together, right? And we have a hole, right? Because this one, because it doesn't have the sharp bit, you can't really drive it in without pre-drilling the hole, right? So you need to pre-drill the hole. So now you got a hole open, and then you basically have the bolt go through, right, like that. And now it's loose, right? So it doesn't do anything. It just comes out, right? So you need essentially the nut on the other end, which you torque in, right? So righty-tighty, right? And then essentially what happens is there's a clamping force imposed by the, well, technically there'd be a washer here to distribute out the pressure, imposed by the nut onto the washer, which goes onto the material, right? And in turn, this bolt goes into tension, if that makes sense, right? That's how it works. So the compression, right? So there's a few things going on. There's quite a few things going on for bolt, right? So one, you torque it, right? So that's a twisting motion, which causes compression from the nut onto the washer onto the material, which causes, so let's just say that's two, and that causes tension. The bolt material itself goes into tension, all that. Okay, are we following? So there's quite a few things that go onto a bolt, but essentially, it's like physically anchored in place. I guess you could say. So these two, yeah, there's an anchor on either side, which is your nut essentially. Okay, I'm gonna move on because I don't see anyone typing in the chat. So, as I mentioned briefly a second ago as well, there's different connection types. So type 1, there's shear connections, and type 2, you have tension or sometimes called withdrawal um, connections. And this is also a stupid thing about the timber code, in my opinion, right? Type 1 and 2, right, there's actually no physical meaning behind why they're assigned shear as type 1 and tension as type 2. It's a completely arbitrary numbering convention, right? But it's what they roll with for the whole of the timber standards. So whenever in this course it says this is a type 1 connection, it's talking about a shear type of connection, right? And then if it says a type 2 connection, it's talking about a tension connection, right? So as you can see from these diagrams, shear connection is where your your connection or your fastener is in shear, right? So essentially you have, again, there's a few things going on, because what will probably be happening is, say these boards are actually being pulled apart from each other, so that's actually tension, right, in the members, right? But the thing connecting the members together, the fastener, this is in shear, right? So essentially it's trying to cut the, well, I've drawn it as a nail. It's trying to cut the nail in half, right? But yeah, that's what an example of shear would be. Here we have tensional and withdrawal. So here's where you have the pulling force happening, and essentially it wants to do this. Oops. Your bit of wood wants to come out like that, and pull the nail, in this case, out with it, right? So that's tensional withdrawal. Another thing to note is, like, this is just one example, but let's just say there was actually compression in the members, right? Like that. That would also cause shear just in the other direction. So that's something else to keep in mind when you're like trying to physically try to understand these systems. We're talking about what the connection is experiencing, not what the members are experiencing. So yeah, cool. Okay, so that's pretty much as far as the theory goes. Everything else is just following rules, so I can go through the rest of this fairly easily. This little note is what I just explained about even if we have like a tension force on the members, it's transferring shear onto the connection itself. And yeah, so here's the capacity equation for the connection. So it's N axial, D is design, so that's where you have all the K factors and phi, and the J here stands for joint. So sometimes it's referred to as the joint strength. And we have all these K factors, which I'll explain in a second. N is the number of fasteners, right? So what happens is your capacity goes up as you have more fasteners, right? Which makes sense, because if you think of this system, for example, going into the page, right? If I have more and more fasteners behind this, right? Just imagine they're like lined up. It would share that external load between all those linearly, right? So yeah, so the number of fasteners will basically linearly increase the strength. And then here's where it gets cooked. You'll see, like I think on the next page, the characteristic capacity of the fasteners. There's just heaps and heaps of tables of this depending on the species of timber, as well as the grain direction and things like that, right? So yeah, it gets pretty confusing there. But let's go through the K factors first. Oh, and then lastly, we're going to have to do the check for it. So you have to make sure the capacity is stronger than your axial force, right? Okay. So capacity factor table. Now I've in the member part of in my week 2 and 3 notes, I actually had a slightly different table, right? So this is my shortened version of the table essentially, right? I think that one was table 2.1, so I was shortening a different table. We have a different table in the standards, which is the capacity factor for joints, right? So instead of listing like MGP and F grade timber and stuff like that here, what's listed are the small connections and large connections, right? So for small connections, these numbers are as such, and the categories are the same as the one you saw earlier in this course, right? And bolts and coach screws have a different rule depending on whether you are dealing with large or small ones. Man, the light the light keeps turning off in my room. One sec. Yeah. Okay. Um, the reason I've highlighted this top row, in red, is because essentially how I've divided up my notes, right, is I want to just have a part. Like, imagine you're taking this into the exam or your midterm, right? It's like a cheat sheet, right? If you're doing a nails or screws question, you only need, like, I want all the available kind of things you need to do a question for nails and screws in one part of my cheat sheet. But if you're doing a bolts question, you have like a slightly different variation. Now, how the code organizes is very annoying because that's where you jump back and forth just for one question. Like, it's really stupid. So it's better, in my opinion, to have everything laid out for the type of question you're doing, right? So that's kind of how I decided to arrange it. And so it's like specifically we're doing a nails or screws question in shear. This is the part of my cheat sheet that you would reference, right? The next one is the load duration factor, which is also different to the last one that you saw, because this one, it's the same table, but it's, if you remember what the table looks like, it's like a different column of the table, right? So yeah, the K1 factors for fasteners. In fact, K1 is actually a modification factor. In the case that you have such a short duration load, like wind load, this becomes an increasing factor, which you don't see for members, right? And this is for type 1 joints, because later you'll see for type 2 joints, you don't use the K1 factor. K1 factor only affects shear joints. But yeah, you should be relatively familiar with the rest of that. K13 is for end grain effects, right? So if you have a bit of timber, just recapping. So block of timber, right? That's the end grain, right? And that's the side grain, etc. Right? So what we're talking about is if you have a connection, right? So you're connecting another member, let's say here, into the side grain like that, right? So you're binding it here together. You have a K factor of just 1. But what happens is if you have an end grain connection instead, that's a good example. Let's say it's like a T joint kind of thing. And it's going into the end grain. That's essentially going to be worse, right? This one. It's only going to have 60% of the strength. So if you think about it, right, and if we continue our analogy that we talked about in week 1, that timber is basically like a bundle of sticks or straws, right? If we have a nail or something going through all these fibers and it displaces it and whatever, essentially, yeah, like, sorry, in shear I should say, let's draw it like this, okay? So there's straws and we have 2 different bits of timber, right? So that's piece 1. That's piece 2. And the nail is going through both, right? In shear, if these are being pulled away from each other, like that, like it basically works the way you think it does, right? But conversely, if you have it going into end grain, right? For example, like this, the nail goes into end grain. What happens kind of at a microscopic level? I'm trying to think of the best way to show this. What happens at a microscopic level, if we zoom in like here, for example, is a nail what's a good way to think about this? It's like, oh, you know those knife holders? Have you seen those like fancy knife holders which have like a bunch of straws? Or like, do you guys know what I'm talking about? It's like a knife block or whatever, and you shove your knife in there. It easily just yoinks out, right? Someone just clapped on Discord. Yes, okay. People are saying yes. People know what I'm talking about. It yanks out because there's nothing to grip onto, right? You're not cutting into any of the fibers, and the fibers basically just like pull apart slightly, right? They just move out of the way for the nail, and so there's really nothing to grip onto. There's nothing mechanically anchoring it, right? And it's purely relying on the frictional strength of the nail into those fibers, which is significantly less, right? So that's why we say it's 60%. Okay, I know that was a long explanation, but that K13 factor comes up a lot in pretty much all of these capacity equations. So yeah, just keep that in mind. K14 factor for the effect of double shear. So what single and double shear is think of a layer of shearing as the interface between two members, right? So that's pretty much it, right? So if you have one interface like that, or if you have two, that's single or double shear respectively, and basically your capacity scales linearly with the amount of interfacing layers you have, right? So if you have two, then you double your capacity basically. That's what that's saying. Okay, basically you can also increase for nails and screws, you can increase your capacity if you have these specific kind of arrangements, which are like plates, right? So you have so I should really have that the other way around. So that's a metal plate. It's a bit misleading. Sorry. So that's a metal plate, and this one's your plywood. I guess like your nail's going through plywood, right? Or if your nail's going through one of these metal plates, you have increased kind of shear capacity, right? If you imagine there's like multiple layers that nail is like shearing through, whatever. I'm not really drawing this terribly well, but yeah, hopefully you know what I'm saying. So it's kind of a similar concept to the double shear thing. Kind of have like multiple shear layers, I guess. But anyway, those are those factors. So K17 is a factor for multiple fasteners, right? So this is basically a reduction factor for if you have too many rows of fasteners because they're not equally contributing. So the best way to explain this and why is if I have like an extreme example, right? So quickly before I draw this out, a row is perpendicular to the force, right? So if the force is going to the right, the rows you can draw as like lines going the other way, essentially. Cool. Okay, so why this is a thing, I'm just gonna exaggerate this, right? So if you imagine this is like elevation view or section view or something. Imagine this goes on for a while, right? We have like 20 rows of fasteners, right? I didn't really, let's say this going like that, and it's connected to another member, etc., right? And they're being like pulled, right? And so you're getting this like shearing, right? The holes, right? For this one, let's say the hole is like that, right? So it's touching the edge. This one's hole is touching the edge. This one's hole is touching the edge. Sorry. I should say the nail itself is touching the edge of the hole that it sits in, right? But what the multiple fastener effect is saying is every now and then you're gonna have one which doesn't like snugly sit on the edge of the hole, and therefore when you pull on it, like this one's basically freeloading. You know what I'm saying? Like it's not doing anything. whereas the rest would be, or like say multiple are doing that, right? So you have to reduce its capacity because when you have too many rows, there's a higher likelihood that there's like slacker, there's like slacker connections, if that makes sense. Like they're not actually physically touching anything, um, in that direction. So yeah, that's kind of what that is. Okay, so moving on to QK. So as I alluded to earlier, this depends on the species of timber you have. But this is different to like what grade it is. Okay, so if you remember, MGP comes in like MGP 10, 12, 15, right? And I think it might go higher. F grade timber, I think it starts at like 6 or 8 or whatever it was, and it goes up. But regardless of its stress grade, it also has a strength group and a joint group, and we're going to be referring to the joint group here, right? So how the coding works, right, is S, if we're talking about strength group, is the strength group, and SD is strength dry, right? The D stands for dry, and that's when it's seasoned. But in our case, instead of S, we're going to be talking about J, which is this joint group, and JD is joint group dry. And if we look at this, right, this is for hardwood species and softwood species in a different table, right? This is also hardwood, by the way. All of the softwoods are like F4. Oh, sorry, there's a few that are 3, right? So they go softwoods go J3 to 6, right? Something like that. I might have missed a few, but generally that's what I can observe. Right, hardwoods go J. I think there's even a few J1s. Yeah, over here, one do. J1 to J. Most of them go to like 4. There might have been like 1-5 or something if you can see it in the list. But yeah, there's like 1 to 4. And so you can kind of see that the lower the number is, the stronger it is essentially. The better capacities it will have. And so yeah. So after you find the joint group, right? So that all those tables were just for finding the joint group. So that's step 1. After you find the joint group, you find the capacity based on whether it's seasoned or unseasoned, right? So there's different fucking tables for both of these. It gets so annoying. So like this isn't even like, it's not even bad yet, right? When we get to like coach screws and like large connections, like bolts and stuff, it's gonna get really annoying. Like these tables like send you around the entire standards, right? So there's unseasoned and seasoned, right? And those will correspond to these joint groups, and yeah, they will specify what nail diameter it is. And just remember, what you see here is in newtons, right? So don't be saying that your nail can take 2700 kilonewtons, right? Out of curiosity, right? People on Discord, in like kilograms, right? So if a dude's like 100 kilograms, how many kilonewtons does he weigh? Sorry to people watching the recording. I'm gonna force an answer out of people on Discord. Oh, sorry. The question was, if he weighs 100 kilos, how many kilonewtons does he weigh? So, I'll just tell you. Let's just say gravity. Let's just say gravity's 10, right? Meters per second squared or whatever, right? 100 kilonewtons is 1,000 newtons, right? And that's 1 kilonewton. Okay, that's like an easy way to remember it. So 100 kilos is 1 kilonewton. So if a fucking if your capacity in shear is the weight of 27,000 sorry, 2,700 tradie blokes who weigh 100 kilos each. There's something wrong. You know what I mean? So yeah, that's how you do it. Um, and is there anything else to say? Not really. So the thing is, it's different for nails and screws. So here's the part where you would see, okay, this is the capacity for a nail, and here's the capacity for a screw. So this is where it's annoying because like if you look at the table numbers, right? Again, you get sent all over the standards. Like if you're doing this without these notes. Um, and so yeah, it's just different set of numbers for screws. Interestingly, like how screws are referred to is like number 4, number 6, number 8, whatever. Um, and yeah, they just refer to how big they are in terms of diameter as well as length. So yeah. That is shear, right? Tension, remember, is calculated differently. So if you look at the formula, it's actually way less, right? There's way less things to consider. Um, you just have to consider K13 and your 5-factor. And now we have something else called length of penetration, right? Length of penetration is that, what you can see essentially. And what you'll see is that instead of, because for the shear, like for the type 1 connections, you get everything in newtons, right? Which you can then convert to kilonewtons. Here we get newtons per millimeter, and we have to multiply it by millimeters, aka that's what LP is, right? And then we get what we want. Then we get our force that we want, right? So that's how this part of the code works. Yep, you've seen this. So K13 is different. So I know I spent all that time explaining type 1 connection and how end grain was like 0.6 and whatever. Now it varies more depending on what kind of scenario you have. So just like before, the best scenario is if you're in side grain, right? Because then it works as intended. And keep in mind, that's not to say that a nail and a screw have the same strength, right? In tension. In fact, someone want to guess in the chat which one's stronger? In tension or in withdrawal? Yeah, that's right. It's a screw, right? So, like I was mentioning earlier, a nail, it gets pulled out, and all it's relying on is the friction, the shaft friction, right? And that's pretty much it. If you have a screw instead, like that, you essentially are engaging all of this timber in like kind of a cone pull-out failure surrounding each of the threads, right? And so you're gauging a lot more material, and it's like mechanically anchored in, right? And so when you try to pull it out, it's gonna have like way more strength, basically. I'm gonna try and undo all this, but yeah. Anyway, so the factor is just one, but the capacity that you'll see later on, QK, is gonna be vastly different. Anyway, a nail into end grain and a screw into end grain behave differently, right? So that factor was 1 for those before, and now its capacity is going to get shafted essentially if you're going into end grain and lose 75% of its capacity, right? Whereas for a screw it only loses 40% in end grain, right? So I'm not going to go through that too thoroughly because we talked about how end grain is just much worse for connections, like if you fix it into end grain. So keep in mind that we fixed it into side grain technically, right? So the material, I guess like where there aren't the threads, right? So where it's just the shaft portion, that is technically side grain, yes. But because kind of the receiving member, the receiving member is the one on the other end of the screw or the nail, right? And that's the one that we're considering, right? And so that's the one that's going into end grain. So actually, as a matter of fact, just to give you an example of what I'm talking about. let's just say we did this instead. Are we going into end grain or side grain? I'm gonna ask people on Discord again, sorry. Okay, I'm gonna give away the answer. We're going into side grain. Okay, because the receiving material is basically on its side. Now there's problems with what I just said because there's like, you know, not enough material there, right? So you kind of want maybe like a chunkier member or whatever, and you probably want more of the threads in the side grain portion if you have a screw. But yeah, anyway, theoretically you're going into side grain if you're doing it the other way that I just drew. Okay, and then lastly we have skew nail into end grain. So this might seem bad because you're reducing it by 40%, but remember this is with nails. This is essentially as good as you're gonna get for nails, and you're kind of, if you think about like this arrangement, right? Instead of going directly into end grain like this, you're doing the next best thing, which is engaging some of the side grain. So if you go in at an angle, this is called skew nailing, right? You can kind of pick up a few of those fibers, and catch it. And so it's like basically when you compare the numbers, right? Having a 40% reduction instead of 75% reduction for nails is quite good. So that's like another alternative essentially. And how those would typically go is I've kind of drawn them like they're in the same plane, but one would technically be behind another, and you would like stagger them, right? So dashed line there is representing that it's like behind the one in the foreground. So this one's in the foreground, and this one's like kind of in the background, and you would kind of stagger it like that. So maybe like top-down view, right? You would have one nail going like that, 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 etc. And that's going into the material, right? Like that. Okay, cool. I'm gonna move on. I see Nathaniel typing here. Do you just use the nail gun on an angle for the skew nail? Yeah, that's right. You can. There are jigs for like if you're doing something more precise, like woodworking. You can get jigs that can put connections like screws and nails at a specific angle. But if you're doing carpentry, it's a lot more like, you know, it's a lot more rough, and speed's kind of the name of the game. So yeah, you just angle your nail gun on an angle. Okay, characteristic fastener capacity. So as I mentioned, this is now a different type of unit. It's newtons per millimeter of penetration, and then later you're gonna multiply it by LP. And so these numbers will look different, right? So if you recall, before we were talking about like I think it was like 2700 or 2400 newtons, right? So you're gonna do that multiplied by how many mil you have, right? Don't get tripped up as well. It says side grain, right? These are the capacity factors for side grain because everything is relative to the side grain, right? So if you have a K13 factor of 1, it's because it's side grain, but it's not that you can't use these tables if you don't have a side grain connection. To do an end grain connection, all you have to do is K13 is 0.6, and you multiply that by your side grain capacity, and that's how you get the end grain capacity. Right, so that would be like quote unquote side grain capacity. Yeah, makes sense. Okay. Similarly organized as the previous table, you've got oh well, sorry. Step 1, you can go back a few pages if you're I made that note for if you're doing this in like a midterm or an exam, you can flip back a few pages to find the joint group. because there's a lot of repetition, right? Um, this is the same step 1 as you saw like 3 pages ago. And then step 2, yeah, these tables are new, which is why. You have screw intention and it's unseasoned, or you have screw intention and it's seasoned, or you have a nail intention and it's seasoned, and yeah, etc. Let's just compare real quick, right? A nail intention, let's just say this top left one. We have 29, right, for nail, this capacity, and kind of like an equivalent shank diameter, not really, they're a little bit different, but similar size, is 81, right? So you kind of have 2.5 times the capacity. Like a screw would have 2.5 times the capacity of a nail intention. So that's essentially like the main advantage of the screw. They behave relatively similarly in shear, I want to say. Let's just compare the numbers quickly. So before we had 1285 and 1720. So yes, like the screw is still a little bit stronger, but only like in shear, but only by 30% or something like that, right? So yeah, much bigger difference in tension that it makes. And lastly, for small connections, we're gonna talk about spacing requirements, edge requirements, and end distances. So D stands for shank diameter here, right? So don't think of it like depth of the member and whatever. Like again, this is where the code's fucking stupidly written. D in this specific scenario means diameter of your fastener, and you just have to make sure you have to make sure it meets all these requirements, right? So that's edge distance, right, from the connection to the edge of the board, or connection to the end of the board, or distance across the grain, or distance along the grain, etc. One interesting thing to note on this page is you're allowed to put your connection closer to your edges and closer together if you pre-drill them, right? So remember what I said earlier. If you just have a nail, or let's just say you have a screw, and you drive it into wood, you're going to displace all the material, right? And that's especially going to have a bigger impact if you are near an edge, right? But if you pre-drill it like that, or whatever, to 80% of the nail, sorry. This only applies to the nails, right? So not for the screw, my bad. So that's for a nail, right? If you pre-bore it to 80%, you're allowed to have these like better requirements. So what happens if you pre-drill it to 180%, right? So let me draw that better. I say 180%, but that's like arbitrary. That's like a number that's bigger than 100%, right? So here's the nail, right? And that's just the diameter. And what you're supposed to do is you're supposed to drill a hole that's 80% of its diameter, right? Because when it goes in, it doesn't displace much material, but has material to grip onto. If you displace it to a hole that's bigger, that's even stupider, because there's no material then to grip onto. Because like the hole is oversized, basically. Yeah, so that's that. Okay. Bolts. So bolts will work a bit weirdly, especially in tension, but in shear they work similarly, I guess, to nails and screws. So again, type 1 is shear. Yeah, a lot of these factors will look similar as when we were doing type 1 connections for small connections. Here we're referring to a different part of this table. That's the same. Metal side plates have a different set of requirements, right? Be effective. You'll see in the tables below what be effective is, but yeah, like there's basically a check you have to do. And then this, I believe these numbers are different, right? But it's the same effect going on. So it's K17. It's a different table that's specifically for large connections rather than small connections. These numbers are different, but the theory is the same. There's also a little note here on what the definition of transverse restraint is. Um, yeah, so basically the code is saying that like if you restrain your timber in a certain way, it could prevent timber shrinkage, and then that is like defined as like your transverse restraint in that case. Find the joint group. So these are the same tables as previous, but I've just pasted it again here for the sake of it being easy to find. But if you print this out, it might be hard to read low-key because I've made the font like a little bit small, but hopefully it still prints out okay. Yeah, so here's where it's a bit different because we're going to have different basically values for if you're dealing with different grain directions, right? So if the timber members are parallel to each other, you're going to be using QSKL, right? So remember QK was your characteristic capacity. Let's say joint capacity. SK, the S stands for system, right? And we're talking about the system, I guess, like it's kind of like a weird naming. I guess we're talking about. It makes more sense like in this context, I think, which is if you have like timber members at a certain angle to each other, the system's working in a specific grain direction, and so you can kind of apply that logic through to if your grain direction is like parallel or perpendicular. It's like a system, I guess. Anyway, so yeah, the tables will say like SKL, which is your parallel one, your parallel system capacity, and then P is perpendicular capacity. And then if you have timber members at a certain angle to each other, you kind of have to do both and compute it in this formula together. So perpendicular and parallel, they'll have different definitions for effective timber thickness, which is what this was in the K16 factor, right? This thing. And honestly, the best thing to do is just read the table. Effective timber thickness is kind of like the minimum of certain things, depending on grain direction, orientation. I don't know. It's kind of a loose terminology, but yeah, you kind of have to follow this table, and it's like a bit of it's a bit stupidly written in my opinion. Anyway, so you know how before for small connections you had the factor for single shear and double shear connections, and double shear connections was like a factor of 2 or whatever. You essentially have the same thing going on here, except it's all within this table. So again, this is where the timber standards are written quite stupidly because it kind of is like inconsistent. It's probably written by different people. So this is like double shear, right? And so it has double capacity. And you just kind of follow that line of logic through for all of this. And if you have like instead of double shear, if you have like triple shear, you sum all of the capacities together, and you'll essentially end up with like the equivalent of triple capacity. But you do it based on like this this effective thickness, and you compare like the layers, and yeah, it's really dumb. Similar idea for perpendicular. And yeah, the effective timber thickness that you worked out based on those loose descriptions in these tables is what you need to basically find the capacity that you're looking for, as well as the bolt size, as well as the joint group. So it's kind of like it's like a 3D table almost, because there's 3 things that you need to be able to read into the table, and then there's also 4 tables, so it's like 4-dimensional, if that makes sense. Yeah. So it's like it's fucking annoying. It's kind of annoying, annoyingly written. Okay. Tension bolts, right? So when the bolts are in tension, now we've introduced more failure mechanisms, right? Um, so the two for bolts, and there's going to be a third one for coach screws, right? But for bolts, you've got your bolt failing, right? So you remember how earlier I was talking about this bolt being in tension itself? Because uh, no, I'll talk about that for the next failure mode. Okay, basically the bolt itself is going to break, right? So this will, because it's like made out of metal, right? If we're just focusing on the bolt shaft, right? It's gonna experience like necking like this, and then eventually like snap and break, right? In tension. So that's kind of what's happening in that first failure mode. And that's simply based on a table, right? This table's pretty handy because it's gonna be able to tell you what the effective area is in the table as well. Here I've just drawn, based on this description here, I've drawn what the effective bearing area is. So you've got the washer and you've got the bolt head, and it's where they're like interfacing is your effective bearing, effective bearing area essentially, right? Um, yeah, the green and the red is basically, I guess all of these. They're all like outputs from this table. So all you need to know is what bolt size you have, and then you already like it just straight up tells you what the capacity of the bolt is. It tells you what the effective area in bearing is, and what minimum diameter you need for your washers. So it's actually a very handy table. Like one bit of information um, tells you like all these things, right? Oh, sorry, it's a minimum required size, but yeah, these are just the numbers that you use in the questions, unless specified otherwise. The second failure mode, you have to compute it like a formula, like how we've been doing it for the rest of it. So these two you should be pretty familiar with. K7 is your bearing factor, which we'll talk about in a second. AW is actually from the above table. So the way it works is this purple one is used for failure mode 1, right? So in this table, they give you what you need to just straight up input into the formula. And this red one, you input into the next formula. So this table will give you failure mode 1 and failure mode 2's kind of parameters, right? Joint bearing strength, yeah, we'll talk about that on the next page. Yep, we've talked about this, we've talked about this. Let's talk about K7 first. So your perpendicular bearing factor is basically your bearing length will correspond to a certain value, which is like an increasing factor unless you're too close to the edge. So if you're too close to the edge, you can't engage enough of the material for this to meaningfully increase your strength. But yeah, it's similar to what we talked about for member bearing strength as well. Oh yeah, Baisu. Okay. Joint bearing strength. Yeah, so this is this value here. Joint bearing strength is just a function of your type of tree and the joint group, and whether it's dry or not. Large connections. Yeah, so we have basically a bunch of rules similar to what we did for small connections on what our ends and like edge distances and stuff can be, and the distance along the grain and between the bolts, etc. But there's just more rules basically, and it gives you the definitions in the code for what L par is, the perpendicular or like the parallel length or whatever, and it gives you what the distance A, which is like the distance between the bolts, I guess along the grain is. Yeah. Anyway, it's a bit dumb, basically. Okay, coach screws. Similar. in type 1 they're similar, and then in type 2 there's an extra mode of failure which can happen. So type 1, yeah, all this stuff you should be pretty familiar with. Yeah, we've seen that. We've seen that. Um, we've seen that. So we also have additional design provisions, and these are more like, I don't really think they'll come up in this course, but they're more like extra considerations you should think about when designing it out in the wild, because it's like there's a few things that you should know before using coach screws, kind of thing, and it's like you should always have washers when you're using coach screws. That's one of the provisions. I think it's this one. And then yeah, like minimum thicknesses and yeah, things that you should be specifying when you're setting up your design. But yeah, I just included that because in case you need it for whatever reason. Timber joint groups, yeah, I've just copied and pasted it from before. You can find like what the tree that you're looking at corresponds to in terms of joint group. Step 2 is figure out what load direction you have, similar to what we did for bolts. And yeah, it's pretty much the exact same concept as before, but it's a different table. So this is why this is why I've included. Sorry. No, it's the same table. It applies to coach screws too, but it's really confusing because the wording of the table says bolts, right? But this in the code it says coach screws. Like this part of the coach screws applies to the this part of the bolts code also applies to coach screws. That's what it says. Anyway. So yeah, we have parallel, we have perpendicular capacities, and these also apply to coach screws as well as bolts, which is confusing in my opinion. So tension, this is unique. These numbers are unique, and this table is unique to coach screws, but it works similarly. So you just grab this number and you plug it into this formula, right? And then failing mode 2, is basically like the withdrawal capacity instead. Oh, I'm getting really sick actually. Just realized. Anyway, so what are we talking about? It's a different formula, and there's going to be like characteristic capacities for coach screws, which can be different to bolts, in tension. And yeah, you kind of just follow through all these formulas. I just realized this doesn't have the washer areas. Okay, I'll correct that in my notes and then fix it. This might be the wrong formula. I'm not sure where AW comes from in this context. It could be the same one as the bolts, and then I'll just paste it here in my notes in the future. Yeah. Okay, that's all that. So here I've done it because I've shown failure mode 2 and it says like next page you should look at all this, and failure mode 3 I say next page you should look at all this. Here's the failure mode 2. Here's the factors which apply to failure mode 2. Here are the factors which apply to failure mode 3. But again, this is pretty repetitive. You've kind of seen all this before, and this is the exact same thing as for bolts. So yeah, that's the end of it. I'll fix up some of the mistakes I spotted as I was doing this, but yeah, that's pretty much it. Thanks for tuning in, and unless you guys in the Discord have any questions, we'll end it there. Oh, one more thing. I think I'll do a week 5 set of notes. It might be a bit of a shorter one, but after that, there's not going to be any more notes from me. Because basically the content isn't being released fast enough. The second half of this course is like different to when I did the course, so I just don't have anything for it essentially. Um, so yeah, so sorry. But if you have any questions, just drop comments, etc. I'll try answering them. Yeah, Nathaniel says I see why the standards are annoying now. Yep. So now you've discovered the dark side of the timber standards. They're just fucking awful. Really inconsistent. Alright, thanks for tuning in. That's pretty much it from me, so I'm gonna stop recording.